Hello again, welcome to Basics of Noise and its Measurement. This is the third lecture for this week, and today we are going to introduce a new topic called reverb time. And this parameter, which is known as reverberation time, you will see later in this week that it will be very useful for all sorts of applications. But the genesis of this reverb time parameter was in context of designing rooms which have better listening properties. So what happens is that if you have a room where there are a lot of reverberations, then when I talk or I speak, and suppose I say the word stop, and what happens is that the moment I utter this word stop, the first part is st, st, second part is a, third part is pa. So I have pronounced sta, and that sound sta reaches your ears. Then I pronounce a, then it again reaches your ears, but by the time it reaches your ears directly, the reflected sound in a highly reverberant room corresponding to sta, it also goes and reaches your ears. So while you are hearing a, you are also hearing sta, and you get confused, and so the perception of sound and speech becomes blurry and unclear. So in that context, people wanted to know what is the reverberation time, how do you quantify this particular parameter, and in that context there were some relations which were developed for measuring reverberation time. So this is what we are going to discuss today, but downstream this reverb time was also used to characterize a lot of materials and for other applications as well. So we will discuss reverberation time. Okay. So at least in this lecture, I am not going to give you a lot of theoretical background, but this relation for this was developed by one scientist or acoustician. His name was Sabine. So that's why the relation which we use to calculate reverberation time of a room is known as Sabine's relation, and the relation is pretty simple. So this is equal to 55 V over A prime C. What is V? V is the volume of room. It is the volume of room. Suppose I am in this room, and this room has to be irregular. What does irregular mean? That does not have to be a perfectly rectangular room. Then this formula may not be very precise. But if there are some obstacles and a lot of furniture is there and the walls are not highly regular and things like that, then this formula works reasonably well. So V is the volume of room, and you can either do it in meter cube or you can also have it in feet cube, but you have to be consistent in terms of units. Then you have A prime, and this is some constant, and it depends on room, and we will figure out how to calculate this constant, but at least for the context of this lecture we will just keep it at that. And this again you can either have it in units are meter square, or the units for this are feet square, but we don't use this term feet square, rather we call it Sabines. Sabines. If I am in the feet system, and then C is velocity of sound, it is velocity of sound, and that is either in meters per second or it is in feet per second. So either I can use these units to calculate room constant or I use these units to calculate my room constant. What is room constant? Because I have introduced this topic, but there is a mathematical definition for room constant. So if I am in a room and I say something, that sound will be heard by microphone directly, that will be the first thing, and the microphone will record some sound pressure level, okay? And then there will be some sound from my mouth which will also go to the walls, it will hit the walls, reflect and reach your ears or the microphone. So that will be reflected sound. Then overall what happens is these reflections keep on happening and your ear keeps on listening to this sound for some duration of time. But after each reflection, the amplitude of the sound goes down a little bit because while it's getting reflected, some of the sound gets absorbed. So after each reflection, the amplitude keeps on going down. So reverb time or reverberation time is the duration over which sound pressure level goes down by 60 decibels. Basically the energy level goes down by a factor of million. So that is what happens, okay? So how do you measure the reverb time of a room? What you do is you have a room, you put a microphone in it and you do some very careful measurement, and then so this is time, and let's say you play a signal, let's say a 1000 hertz tone. So your 1000 hertz tone, you play and you keep on playing it for some time so that everything becomes steady, and then you stop the signal. And then what happens, this tone as sensed by the microphone, it starts decaying. So your tone starts decaying. So you make this recording of the pressure signal and then you say, okay, this is my P max, and then it has decayed maybe after time. So from this P max I start counting time, and then the duration it takes for this P max to go down by 60 decibels, that is the time which I identify, and then I say that that is the reverb time of the room. Okay, so that is how I physically measure the reverb time of a room. But I can also calculate the reverb time of a room using some other methods. So I calculate that the reverb time of the room using this formula, 55V over A prime C, and we will discuss this further. So we had written that reverb time of a room is 55V over A prime C, and then you will say what is A. So A prime is equal to S natural log of 1 minus alpha. Okay, actually it's alpha bar. And what is S? S is the surface area, internal surface area of room. So you take all the walls and all the shapes inside the room and you calculate the surface area, internal surface of the room. So that is your this thing. So this is in meter squares, or it could be in feet square, and alpha is the absorption coefficient of room. And it is a dimensionless quantity, it has no dimensions. So the dimensions of A are mathematically same as that of S, but in foot-pound system, at least when we prescribe A prime, we call it Sabines. But mathematically it would be foot square, but the proper term to use is Sabines, because it's not the internal surface area, it is that multiplied by natural log of 1 minus alpha. So if I know S, which I can very easily calculate for a given room because I can measure, and if I know alpha bar, then I know A prime and I calculate T. But then what is alpha bar? So alpha bar is given by another relationship, S1 alpha 1 plus S2 alpha 2 plus S3 alpha 3 till keep on doing this over S. So this is the formula where S1, S2, Sn, they are all surface areas of, they are areas of individual surfaces. So if I have a room which has 7 or 8 internal walls, then or surfaces, roof, floor, different walls, door, window, I have to calculate each separately. Then I calculate the area of each of these in meter square and make a list of those. And then what I do is I find out alpha 1, alpha 2, alpha n. What are these alphas? These are absorption coefficients for each surface. Okay. So you have to identify each surface in the way that it is the material of that surface has to be same. You cannot club the surface of a window with that of a wall, because the absorption characteristics of window may be different than that for the wall, than that for a curtain. Suppose there is a wall covered with a curtain, that's a separate thing, because there you have to calculate, you have to find the absorption characteristic of the curtain. If there is a wall without a curtain, then you have to find out or identify the absorption characteristics of the wall itself. If you have a floor which is of wood, it's a different surface. Okay. So if you know these alphas, alpha 1, alpha 2, alpha 3, alpha and all these, then you can calculate the numerator, and S is nothing but S1 plus S2 plus S3 Sn. S is the total surface area, internal surface area of the room. Okay. So again, so I can very easily find out S1, S2 till Sn. I can calculate S. So the only thing now we are missing is, how do I know what are alphas? If I know alphas, then I can calculate this A prime. From A prime I can calculate the reverb time. Okay. So that is finding. So this you do not calculate, you find it. Alpha I for the ith surface. And what do you do? So first thing, we will actually show some tables. One thing to understand is that alpha is the absorption coefficient, and we had discussed this earlier also, that it can change with frequency. So typically we identify alphas at 5 or 6 standard frequencies. So what are these frequencies? Finding alphas, standard frequencies which you measure them at 125 Hertz, 250 Hertz, 500 Hertz, 1000 Hertz, 2000 Hertz and 4 kilohertz. Okay. At these different frequencies you try to figure out their values. and then for each frequency you have a different value of reverberation constant for the room. So your reverberation constant changes from frequency to frequency, and these, for each frequency you can find the value of alpha from some standard literature which is available in books or data sets and things like that. So I will show you one example. Okay, so these are the absorption coefficients for general building materials, and this is I have taken this information from this text Acoustics by Berenek, and what you have is a table. The part of the table is also produced here. So suppose you have an unpainted brick wall and it is 18 inch, 1.5 feet thick, then its absorption coefficient people have determined at 125 hertz it's 0.02, 250 it's 0.02, 500 it's 0.03, and so on and so forth. Let's look at something else. Suppose on the floor you have carpet, then what is the absorption coefficient for carpet? You can have two types of carpet: woolen carpet with underpad if there is a lining below it, then at 125 it's 0.2, 250 it's 0.25, at 500 it's 0.35, and so on and so forth. If you have curtains, so you have draperies and different types of draperies, so they are also mentioned here. If you have a wooden floor, it could be solid and polished, or it could be a panel. So again their absorption coefficients are listed here. If you have a plastered wall with a plaster, then again you have. So the point is that there are all sorts of materials which are used to make rooms. If you have a glass, then this is the absorption coefficient. Okay. So using this table, or if you have some special material, you have to identify what is its absorption coefficient. Then once you have done this, you can calculate all the values of the value of this alpha bar. From alpha bar you calculate A prime, and from this you calculate the reverberation time of the room. So that's a fairly straightforward process. Now there may be some cases where suppose you have an auditorium, so there are lots of chairs, and you can have two situations. What is the reverberation time when there are no people inside the room, and what is the reverberation time when there are people inside the room, and that can change significantly. So if there are people inside the room, then the relation for alpha bar, it changes somewhat. So what is it? It is alpha 1 S1 plus alpha 2 S2 plus alpha 3 S3 plus, so this is the same stuff which we had seen earlier, plus we will put some other term, and that is N times alpha P divided by S. Okay. So alpha P is absorption coefficient of a person, and N is number of persons. The definition of S does not change, it is still S1, S2, S3 till Sn, but in the numerator we have this extra term. So there are people have taken measurements on these parameters also. So let's look at that. So this is people, okay, and it depends whether it's a person or a child. I mean, it's a big person or a child, and if the person is sitting in a regular chair or a chair with a lot of gaddi and upholstery, then the absorption coefficients are different. If the persons are seated, or if they are standing, or if there are seats with no cushions, so there are all sorts of situations. So using this you can find the role of people on the absorption coefficient also, and you can calculate this thing. So once you have calculated the reverberation time for a room, then you would like to see whether it meets your needs or not. Okay, so mathematically you have calculated it, and let's say that you are in an auditorium and you are designing an auditorium and you want to make sure that for the needs of the auditorium you have the right reverberation time. So then there are some guidelines to figure out whether the calculated reverberation time is correct, appropriate for that application or not. So there are again some more tables. So this is one table, and let's look at this table. So you say this column is usage, okay. So I can have a room where I am just talking, regular speech, or I can have a room which is like a movie theater, or where lot of music is played, or an auditorium, or some regular music is played. And then this room could have different sizes, 10,000 cubic feet, 1 lakh cubic feet, 10 lakh cubic feet, and so on and so forth. So recommended reverberation times for rooms of different sizes, and this is again at 512 hertz. So you calculate in 512 hertz and see that if your reverberation time is close enough to this, then maybe you have done a good design, okay. So you have a table like this, or you can have charts like these also, okay. So on the x-axis you have volume of the room, and on the y-axis you have reverberation time. So you have one curve for classroom, another for theaters, another for multipurpose, and so on and so forth. So this is not necessarily the final word. There are more guidelines and more recommendations, but the point is that once you have this reverberation time, then you can make sure that verify whether it meets your needs or not. This is another table, okay. So what does it say? Reverberation time for common applications. If it is between 0.8 and 1.3, then it's good for speech, where people are just having conversation. But if it is between 1.4 and 2, then for speech purposes it is not good enough. If it is higher, then it is unacceptable, and the optimum value is somewhere here, okay. For contemporary music, so again there are some recommendations. For choral music, there are again some recommendations. So you will have to figure out what will be the right reverberation time for your need. But the calculation of the reverberation time will be based on the relationship, the Sabine's formula, which we have discussed till so far. So this is what I wanted to discuss in this particular lecture, and what we will do in the next class will be an extension of this, and we will introduce this thing, anechoic chambers, noise reduction coefficients, sound transmission coefficients, some of these terminologies. So that's what we are going to cover in next couple of lectures. But today's discussion, I think it is over, and we will see you tomorrow. Thanks.